everyone. This is a mini lecture on some chemistry and physical principles as they relate to respiratory therapy. So let's first start with atmospheric and alveolar gases and what they mean. When we talk about atmospheric gases, this is ambient air, what you're breathing. It's comprised of 78% nitrogen, 21% oxygen, actually it's 20.8, but we round up to 21%, 0.95% argon, and 0.05% carbon dioxide. These gases together exert pressure on the Earth's surface, which is what we call barometric pressure or ambient pressure. As you probably know, barometric pressure decreases with increasing altitude, and that's because the densities of the gases change. The molecules are further apart from one another per unit of volume. But the percentage of gases do not change. So if you think about the term FiO2, fractional inspired O2, as you climb in altitude, the FiO2 does not change. It's still going to be 21% oxygen. It's just that with each breath, you're pulling in a smaller number of oxygen molecules. And each of these gases in the atmosphere will behave according to the gas laws. And I'll talk more about the gas laws in a little bit, and specifically the ideal gas law. Now, we want to think about alveolar gas, and we'll talk more about that in a minute, but consider alveolar gas as being 100% humidified. And this is at absolute humidity equal to 44 milligrams per liter. This is a number that you want to memorize. That will give a water vapor pressure of 47 millimeters of mercury, regardless of the humidity of the inspired air. Now, I'm sure you guys have already learned this when we were talking about some of the calculations for your case studies. You also want to keep in mind that as temperature decreases, this is temperature in the body also, absolute humidity could decrease. And therefore water vapor pressure also decreases, and vice versa. This is why it's important to make sure that when somebody is intubated, that the gas going through the endotracheal tube is adequately humidified and has the right temperature to avoid excess workload on the body to maintain temperature and volume homeostasis. So let's move on to these alveolar gases. We talked about barometric pressure, which is the same as ambient pressure, which is also the same as alveolar pressure when there's no movement of air. That means if I'm holding my breath in or holding my breath out. But the difference lies in the percentage, not the percentage, but the independent partial pressures of each gas. So atmospherically, outside of your body, oxygen partial pressure is about 159 millimeters of mercury. But in the alveoli, it's 100 millimeters of mercury. So why does it decrease? Well, it decreases because the alveoli can only hold so much volume and pressure. And as you know, carbon dioxide is coming out of the capillaries into the alveoli. So that carbon dioxide partial pressure will be higher in the alveoli than it is in the atmospheric pressure, taking up more space or pressure room, if you will. And the P big A, and big A stands for alveolar, carbon dioxide is about 40 millimeters of mercury. Now, the partial pressure of oxygen is also lower in the alveoli compared to ambient air because it's diluted with water pressure, which is, as we mentioned in the previous slide, about 47 millimeters of mercury. Now, when this slide is working properly, the box with the blue dots in it are moving and bouncing off of each other. They don't combine. And that's what an ideal gas is. They're gas molecules that can collide, but they will not form a new molecule. They will stay in their inert state. So if one was an oxygen and one was a carbon dioxide, when they bump into each other, they will not produce a new molecule. They will just bounce off and remain their oxygen and carbon dioxide molecule. Now, if we look at the figure to the right, it's representing an alveolus. And the light blue or turquoise represents nitrogen. And obviously that takes up most of the space in the alveolus. And then in yellow, we have water vapor pressure. And then in blue, we have carbon dioxide pressure. Now, those lines are not obviously to scale, but you get the idea of how they're taking up space. And then there is oxygen at 100 millimeters of mercury. So this is why oxygen in the alveoli is less than that in the atmosphere. And why carbon dioxide in the alveoli is also less than that, or is greater, is greater than that in the atmosphere, because the carbon dioxide is coming from the capillaries. So if we think about a physical principle or a law that we can relate to alveolar gases and the partial pressures, Dalton's law is it. And that's what's represented here as alveolar pressure equals the partial pressure of alveolar oxygen plus the partial pressure of alveolar carbon dioxide plus the partial pressure of alveolar water or water vapor plus the partial pressure of nitrogen. Now it's the P big A alveolar O2 that we're looking for in what we call our alveolar air equation. So we could get that from Dalton's law, but you'll learn that Dalton's law is also really a component or comprised of the ideal gas law. So you can see the formula here for partial pressure of alveolar oxygen is equal to barometric pressure minus water vapor pressure. And we will always use the water vapor pressure of 47 millimeters of mercury. The barometric pressure, if not given to you on a test, will be set at 760 millimeters of mercury, which is sea level and also equal to 1 atmospheric pressure. Now, if you're in clinics or you're doing a case study, you want to look up the barometric pressure of that area for that particular day because it changes. So the barometric pressure minus the water vapor pressure is the first part of this equation. And we multiply that by the FiO2, which is the inspired fractional oxygen level. So if somebody's just breathing room air, that's 21%. If you have them on oxygen, then you have to calculate what FiO2 they're receiving to add to this equation. So that part of the formula would be done first. You can see it's in brackets. And then the second part of the formula would be the carbon dioxide measured from the artery, which is what the small a stands for, times 1.25 or divided by 0.8. Mathematically, they are equal. So you can do either or. Once you do the first half of the equation, which is in brackets, and then the second half of the equation, which is the PaCO2 times 1.25 or divided by 0.8, then you subtract them together, and that gives you your alveolar oxygen, partial pressure of alveolar oxygen. So let's talk a little bit more about Dalton's law of partial pressures. And this is a perfect example of it, because you can see it in a jar. It makes sense. So in this story, PT is the total pressure of a sample, which contains a mixture of gas. So that would be depicted in part C of the figure on the far right side. Now the mixture of gas is equal to the partial pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3, etc. And they're all added together to create the total partial pressure. If we look at our example in figure A, this is, we're keeping the volume and the temperature constant. And what is going to change here is actually the partial pressure and the molar concentration. So the first figure A here shows a partial pressure of hydrogen of 2.9 atmospheres. And that 2.9 atmospheres here is made up of 0.6 moles of hydrogen. So I think that you might need to go back to basic chemistry and remember how to convert moles, atoms to moles, moles to grams, and back and forth. I would definitely be looking that up if I were you. And we'll add that as homework 1. Now, if we look at the figure B here, you can see that we have a partial pressure of helium of 7.2 atmospheres. And that 7.2 atmospheres is made up of 1.5 moles of helium. When we add the partial pressure of hydrogen to the partial pressure of helium, that gives us a total pressure of 10.1 atmospheres. We just added them together. And then that total pressure is comprised of 2.1 moles of this gas, which is a mix of helium and hydrogen. This is Dalton's law. So let's expand Dalton's law into components that are really the ideal gas law. So on the left side here, you see PT equals P1 plus P2 plus ... This is the Dalton's law that you saw in the previous slide. But how are those pressures calculated? Well, each pressure is equal to N times R times T divided by V. So we're looking at the moles times a constant, and we'll talk about that in a minute, times the temperature of the system divided by the volume of the system. So this is how you would calculate the pressure of each one of those gases that you add to a total pressure when using Dalton's law. And we can keep it as simple. We can keep it as N1 times R times T divided by V, being for pressure 1, and then plus N2 RT divided by V as pressure 2. Now, I gave you a link here that gives you the opportunity to practice some of these problems. So be sure to write it down and look those up. And let me know that you've done that. So that will be homework 2. All right, so let's think about the components of this equation. The R's are constants, and depending on which units you're using in your calculations, we will use 8.3145 if we're using joules per mole times Kelvin temperature. And that's Kelvin temperature. So I think you might need to learn how to convert Kelvin to Fahrenheit, to Celsius, etc. If we're using liters times atmospheres times Kelvin, then the R that we will use will be 0.0821. So these are numbers that you want to memorize. You're going to use them. A lowercase n represents the number of moles. An uppercase n represents the number of molecules. And the K, which we'll talk about in a little bit, is Boltzmann's constant. And that'll be given to you. But a lot of times, because it's constant, we just cancel it out. So if you look up at the top, where it says ideal gas law, you can see pressure 1 times volume 1 divided by T1 is equal to pressure 2 times volume 2 divided by temperature 2. So this is the calculation, but we have taken out some of these other variables because we're assuming they're constant. Now, that's not always the case. So if you're given moles to calculate pressure, make sure you know how to convert them. So looking down at the bottom here where it says ideal gas law, it is commonly written in this way for respiratory therapy type problems where pressure times volume is equal to moles times the R constant times temperature. And you'll rework that equation algebraically to solve for the parameter that you're looking for. So make sure you practice that algebraic equation manipulation. So the ideal gas law can be further broken down into three components. And in each one of these components, one of the variable will be constant. So Gay-Lussac's law is basically pressure 1 divided by temperature 1 is equal to pressure 2 divided by temperature 2. So pressure and temperature are directly proportional. That means that as one goes up, the other also goes up. As one goes down, the other also goes down. And in this equation, you notice that volume is missing because volume is assumed to be constant. So your homework number 3, Gay-Lussac's law. Figure out how you can apply Gay-Lussac's law to something in your life. It doesn't necessarily have to be related to respiratory therapy, but make it functional. Learning how these parameters or variables work together or against each other or with each other is important for learning how to apply these. So think about it. What kind of system or situation can you use to explain Gay-Lussac's law? And in that scenario, you would have a situation where pressure increases as temperature increases, or vice versa. And moving on to Charles' law. So here we have volume divided by temperature is equal to volume divided by temperature. We've got volume 1 and temperature 1. Volume 2 and temperature 2. Here, pressure is constant. It's missing from the equation. And again, here, volume and temperature are directly proportional. Come up with an idea or concept that allows you to make this functional. Now, one thing I want you to think about in regards to Gay-Lussac's law and Charles' law is how molecules function. If you have a container of molecules and you increase the temperature, that's going to increase the kinetic energy of those molecules. It's going to make them move more. And that movement in itself will increase the pressure in the system. And as they move, they may actually also increase the volume if they're moving further away from one another. So think about kinetic energy as it relates to temperature, altering pressure and volume. But that's just one example. Come up with something that makes sense to yourself. So that's homework question number 4. Make Charles' law functional to you. Apply it to something in your life. And then we have Boyle's law. And this one's my favorite. And we can get real complicated with this. But Boyle's law is pressure 1 times volume 1 is equal to pressure 2 times volume 2. So they're inversely proportional. So as one goes up, the other goes down. As pressure increases, the volume decreases. As the volume increases, the pressure decreases. So they go in opposite directions. So I would like you to take this and apply it to something on your own, but I would also like you to take this and try to apply it to the concept of lung compliance. Now remember, when we use the term lung compliance, it means the ability to accept volume at a given pressure. As somebody's compliance decreases, that means one of two things. More pressure is required to deliver a set volume, or at a set pressure, less volume is delivered. How can we take that and apply it to Boyle's law when it seems the opposite? It's not a trick question. You just have to think about physiological concepts. All right, now let's talk about the phase diagram. The phase diagram represents pressure on the y-axis and temperature on the x-axis, and it's basically showing us the different states of matter. So on the left side, we have solid. On the top middle, we have liquid, and on the right bottom, we have vapor. The triple point there is the point at which all three of these states of matter occur at the same time. Now, this is the phase diagram for water. And we'll put some numbers to it in the next slide. But I want you to consider the terms melting, boiling, sublimation, evaporation, and condensation. Where could you plug in those terms as it relates to a position on this particular diagram? I'll give you a hint of what I mean. If we're talking about melting, then I would look for a temperature and pressure that lines up somewhere. Let me get my pen going here. Give me 1 second. Looks like it's going to freeze, of course. Okay, here we go. Draw. Okay, so I'll do the first one for you. Melting. We know that melting means that something is changing from a solid. I'm sorry, my pen is frozen. It's not working very well. Okay, from a solid to a liquid. So anywhere in this area, we would possibly experience melting of water. So you want to recognize the pressures and the temperatures at which that solid would change into a liquid. Okay, so think about that. You guys do that for boiling, sublimation, evaporation, and condensation. Right, now, here's a comparison of, let me move this out of the way. Here's a comparison of water and carbon dioxide pressure to temperature curves showing their triple point. So on the left side, we have water, and at 1 atmosphere and 0 degrees Celsius, that's where, along with some other points, solid water will turn into a liquid. And then at 1 atmosphere and temperature of 100 degrees Celsius, that's when that water liquid turns into a vapor. So that's boiling. Now, if we look at carbon dioxide, it's quite different. At 1 atmosphere, solid carbon dioxide goes straight to a vapor. What is that called? I'm sure you learned that. You'll learn that as you do your homework. Negative 80 degrees Celsius and what atmosphere is the point at which solid carbon dioxide will turn into a vapor. So if I were you guys, and we'll make that question number 7, what do the curves look like for, you have water, carbon dioxide. Let's add oxygen because we're really interested in oxygen. Let's add helium because we're interested in helium. And let's also add nitrous oxide, N2O, nitrous oxide. What do those curves look like for oxygen, helium, and nitrous oxide? I gave you water and carbon dioxide. You'll look up the other two. We also need to talk a little bit more about energy. So here, KE stands for kinetic energy. And the standard formula for that is 1/2 times the mass times velocity squared. So that's the movement of a molecule or whatever, an object. And kinetic energy means movement, energy in motion. Keep that in mind. And then we have potential energy. And the physical principle that's related to that is mass times gravity times height. So here you could think about somebody holding a ball up above their head, and they haven't released it yet. The energy that's in that ball waiting to become active as kinetic energy is equal to how much it weighs and the gravitational pull and how high it is. Now, there are some other types of potential energy that we're going to talk about here. Think about thermal energy. As soon as you put your hands together and then you begin to move them, so potential energy was when you put your hands together, and then when you begin to move your hands together, rubbing them together, that's kinetic energy. But that kinetic energy actually produces thermal energy also. Do that and you can feel that heat. And then we have electrical energy, which is positive, negative charges that can create a current. And chemical energy. So think about what you learned about ATP. We talked a little bit about that in class. Let me get my marker here. ATP, you know this as the main energy molecule. But the A stands for adenosine. What exactly is adenosine? That's question number 8. What is adenosine? And the cool thing about adenosine is that you can identify it as one particular type of thing in the body, but it serves so many different functions. It's pretty wild. So this adenosine can bind to phosphates. And when we have ATP, the T stands for tri. So 1, 2, 3 phosphates. Now, when this bond between this phosphate and this phosphate is cleaved, broken, that provides chemical energy. So while you're looking up ATP, look up adenosine, look up ADP and AMP, and think about the functions that they may serve. And then, of course, we have nuclear energy. Think about what that might mean and how you can apply it. Now, I'm sorry that my figures are not working for you, but what you should see over here to the right in the circle is all of these circles vibrating together. They kind of zigzag in an irregular motion, and this is common in minute particles that are suspended in a fluid. And this effect is observed in all types of colloidal suspensions. It doesn't matter if it's solid in a liquid, liquid in a liquid, gas in a liquid, etc. We have this, what we call Brownian motion. And this Brownian motion, the effect of this Brownian motion is independent of all external factors. It's ascribed to the thermal motion of the molecules of a fluid. The molecules are in a constant irregular state of motion with a velocity that's proportional to the square root of temperature. And Brownian motion is observed for particles that are about 0.001 millimeters in diameter. They're small enough to share in the thermal motion, yet large enough to be seen with a microscope. Now, if you think about a cell and the cytosol, which is kind of a liquid inside a cell, and you have all these enzymes and carrier molecules and signaling molecules inside a cell. How do they get around? How are they attracted to one another? Well, the cytosol helps because it acts as this liquid, allowing the concept of Brownian motion at that level. But at the same time, the positive and negative charges of all of those, we call them peptides or proteins, play a role in how they're going to associate with other proteins, other peptides. And this is a very important thing to think about. Our body is regulated by positive and negative charges. It's so complicated, but so simple as that. It's so interesting. Now, a little bit about thermal equilibrium. You're going to do some more homework on this, and I apologize for my heater picture not showing today. I don't know what's going on with my figures, but keep in mind, heat flows to cooler regions. And you guys have probably noticed that with your coffee cups. We've got 3 different types of mechanisms by which thermal equilibrium can occur. We have conduction, convection, and radiation. Conduction is defined as heat transfer through atomic collisions. This can occur in a solid or a liquid. Convection is heat transfer by movement of masses of material and can occur in solid, liquid, or gas. And radiation is heat transfer via transformation of light into motions of atoms and molecules. So for your homework number 9, give me some examples or one example of conduction and how you can relate that. Convection and radiation. Now, the term absolute zero refers to what people perceive as the point reached when all oscillations or vibrations are the slowest they can possibly be. That temperature is what we call absolute zero. 0 Kelvin, negative 273 Celsius, or negative 459 Fahrenheit. But interestingly, oscillations really never come to a complete stop, even in absolute zero. So is there really an absolute zero? Yeah, you guys want to learn how to convert Fahrenheit to Celsius, Celsius to Kelvin, Kelvin to Fahrenheit, etc. And you want to memorize water boiling at 212 Fahrenheit, water freezes at 32 Fahrenheit, and those are equal to 100 degrees Celsius, 373 degrees Kelvin, 0 degrees Celsius, and 273 degrees Kelvin. You want to have these in the back of your mind. You're going to use them in calculations. So for question number 10, show me examples in which you have converted all the different ways temperature can be expressed. So Fahrenheit to Celsius, Fahrenheit to Kelvin, Celsius to Fahrenheit, Kelvin to Fahrenheit, Kelvin to Celsius, Kelvin to Fahrenheit. These are very easy to look up and they're also in your textbook. Now, let's talk about density a little bit. We talked about temperature playing a role in increasing the pressure or volume by increasing the kinetic energy of molecules, causing them to move more and spread out. But what you also want to keep in mind is that changing the temperature does not necessarily change the weight. It does change the volume of the substance by expansion or contraction, thus changing the weight mass per unit of volume. So the key here is per unit of volume. And this is what we call density. Density is equal to mass divided by volume. So if we look at case 1 here, the mass that these molecules make up is 0.52 kilograms. And the volume is 2 times 1 times 1, which is equal to 2 meters squared. 2 meters cubed, excuse me. If we do the math on that, which would be mass divided by volume, 0.52 divided by 2, then that gives us 0.26 kilograms per meters squared. If we look at case 2, we're just looking at a certain area of the container. The mass is still 0.52. The volume is still the same, and the density comes out to be the same. Now, if we were to change that and decrease the volume, we would have a decrease in mass simply because there's less molecules in that box. When we look at case 3, we still have a mass of 0.52 kilograms, but the volume is significantly decreased. It's 1 meters cubed. And doing the math, we get 0.52 kilograms per meters cubed. This means the density is increased. So in case one, the density is less because there's more space for those molecules to float around. In case three, the density is more because there's less space for the same number of molecules to float around. Now, when we look at case four mathematically represents what we see in the top box. The density of the case 2 and case 4 box is exactly the same. The only difference is we took a lower volume of the mass, the lower volume of the container, which thus will have less mass in it because it was spread out. So it's the same thing. Case 4 is basically the blue box in case 2. So let's relate density to specific gravity. And specific gravity and density kind of mean really the same thing, except we're using the concept of weight instead of mass. And if you're a physicist, you don't like to mix those terms up, but we'll use it here. The ratio of the weight of a unit of volume of some substance to the weight of an equal volume of a standard substance measured under standard pressure and temperature conditions is what we call specific gravity. So you can see it in a formula form there. Specific gravity is equal to the weight of a substance divided by the weight of an equal volume of water, water being our standard substance. And then we would have experimental conditions to keep the pressure and temperature constant or be standard also. So we can translate this as a density also. It's the same idea. Density of the substance divided by the density of water is equal to the specific gravity. The specific gravity of water obviously is 1. So when we think about urine and we're doing a urinalysis, understanding how density plays a role in helping us understand how many molecules that are large are in the urine abnormally can give us an idea of how well somebody is hydrated or not, or whether or not their kidneys are filtering properly, or whether or not there's kidney damage that can cause, extra filtration of proteins through the kidneys, which is not normal. Now, the same types of formulas are used to find the specific gravity of gases, but you just simply substitute air, oxygen, or hydrogen for water as your standard substance. Okay, so quiz 2, or quiz 3, because you have 1 and 2 on the last week's presentation. You have a 40-year-old man with a history of myocardial infarction, status posed 2 years ago. So he had the heart attack or myocardial infarction 2 years ago. And he has a history of alpha-1 antitrypsin deficiency. His blood pressure is 72/42. His heart rate is 120. His respiratory rate is 8. And he has peripheral pallor. Breast sounds, 5 basilar crackles. And the chest x-ray shows increased hilar markings. That means we can see the blood vessels better than normal. His blood gas, pH 7.24, CO2 48, O2 42, and bicarb 16. So I'd like to know, what do you think is going on with this person? Why? And also interpret the blood gas. What would you like to do? And then we have a 24-year-old female, status post motor vehicle accident. She's unconscious. Her blood pressure is 90/73. Her heart rate is 160. I apologize for the typo there. Her respiratory rate is 20 and shallow. She has a deviated trachea, decreased breath sounds on the right, and unequal chest excursion. What do you think is going on, and what are you going to do about it? Again, I apologize for the typos. That should be 90 divided by 73 as for blood pressure. I would calculate the MAP there and pulse pressure to see what's going on there. That might give you some hints. So I'd look up MAP, pulse pressure, be able to calculate them and interpret them based on this blood pressure. And the heart rate is 160, respiratory rate 28. Okay, now let's talk about the alveolar capillary membrane, and that is where the alveolus comes in contact with the capillary. If we look in the alveolus here, you can see that alveolar oxygen partial pressure is about 100, carbon dioxide is about 40, water pressure is about 47, and nitrogen is about 573. So you've seen this in a previous slide. And you can see that those numbers changed relative to the conducting airway because of the differences in water pressure and carbon dioxide relative to ambient air. Now, on the left side of this screen, when we're looking at the capillary, you can see PVO2, and here you see a line over the V. That represents mixed venous. So this is partial pressure of mixed venous oxygen, and it's 40. So this is coming from the body to the alveolus to get oxygenated. And we have a partial pressure of mixed venous carbon dioxide of 46 millimeters of mercury. If we think about the driving pressure between carbon dioxide and oxygen, the alveolus, we have 100 millimeters of mercury oxygen. But in the capillary, we have 40 millimeters of mercury. That means we have a driving pressure of 60. So oxygen is going to diffuse through that alveolar capillary membrane pretty nicely because it's kind of nice, strong driving pressure. It's wide, it's 60 millimeters of mercury. Carbon dioxide, on the other hand, in the capillary has a driving pressure, has a partial pressure of 46. And in the alveolus, which is where it needs to go, it's only 40. So there's only a driving pressure of 6 millimeters of mercury here. So carbon dioxide doesn't diffuse through there as much. Now think about this. If somebody has emphysema and their alveoli cannot retract back to the resting state, and therefore carbon dioxide cannot be pushed out of the alveolus, over time, that alveolar carbon dioxide level will be higher than 40. And this ultimately will decrease the driving pressure. And this is when we see people with hypercapnia. Now, as we look on to the right side of that capillary, you can see P(a)O2, that's arterial oxygen. It's about 97 here, and the PaCO2 is about 40. So this is normal. Now, let's think about the time allowed or available for this gas diffusion to occur. Equilibrium, that means that you're equalizing what's in the alveolus and the capillary, moving oxygen into the capillary and carbon dioxide into the alveolus. This equilibrium is reached in about 0.2 to 0.25 seconds. But the total time blood moves through this alveolar capillary membrane area is about 0.75 seconds. So there's plenty of time for gas diffusion to occur. And normally, under normal circumstances, no pathology to the alveolar capillary membrane, and diffusion is accomplished in about a third of this time. So it's perfect. During exercise, this time is going to be decreased because cardiac output is faster. But it's still more than adequate unless there's a disease process, such as pneumonia causing consolidation or fibrosis causing thickening of the alveolar membrane, pulmonary edema increasing the space between the alveolus and the capillary by increasing interstitial fluid, etc. So brainstorm about different things that can decrease alveolar capillary membrane function. These are things that you'll want to talk about. Now, let's take this a little bit further. And I believe you guys have seen this formula before. We're looking in the erythrocyte, the red blood cell at the top. This red blood cell is at the tissue level. And you can see carbon dioxide is diffusing from the tissue cells through the interstitial spaces, through the endothelium, through the plasma, into the erythrocyte. And when that carbon dioxide gets into the erythrocyte, it binds to water. And if carbonic anhydrase is present, this reaction will be increased because that's an enzyme that decreases the time needed for the reaction to occur. So it's happening faster. So carbon dioxide plus water will combine to produce carbonic acid and then break down into bicarbonate and hydrogen ions. Now, carbon dioxide will also bind to hemoglobin. It doesn't bind to hemoglobin the same way as oxygen does, and we'll talk about that a little bit more later, creating HbCO2 or carbaminohemoglobin. And of course, hemoglobin binds to oxygen as well. Now, in this situation, at the tissue level, hemoglobin is going to release oxygen so that that oxygen can diffuse through the erythrocyte, through the plasma, through the endothelium, through the interstitial tissue fluid, and through that tissue. So it can get into the mitochondria where it participates in oxidative phosphorylation. Now, still looking at the red blood cell on the top at the tissue level, you can see that hemoglobin can also bind to hydrogen. That's what HHB stands for. And that is something that helps play a role in regulating where hydrogen ions are going to be released and not, and vice versa. Now, at the same time, you can see that bicarbonate has a tendency to diffuse out of that red blood cell. And as a replacement, chloride moves in or diffuses in. So this chloride shift is an important physiological concept. So keep this in mind. Now, a lot of people are told that this activity of carbon dioxide binding to water to produce carbonic acid only happens in the erythrocyte because of carbonic anhydrase, but that's actually not true. It actually occurs also in the plasma, as you can see there. And a lot of people will say that carbonic anhydrase only occurs in the red blood cell, but there's many different isoforms of carbonic anhydrase, and they do many different things. So that'll be something fun to look up, but you don't have to do that for now. I just want you to learn this particular figure. This figure you should be able to write an essay about. As a matter of fact, why don't we make that question number 3? Writing an essay about this figure. Now, once that erythrocyte picks up the carbon dioxide and has released the oxygen, cardiac output perfusion is responsible for getting that erythrocyte to the alveolar capillary membrane, where it now, if we look at the bottom erythrocyte, can release carbon dioxide. And that release of carbon dioxide comes from the breakdown of carbonic acid. So bicarbonate plus hydrogen ions breaks down into carbonic acid, which will break down into carbon dioxide and water. So from that, you should think a lot of the carbon dioxide picked up at the cellular level is carried in the blood as bicarbonate. I hope you guys got that. A lot of the carbon dioxide carried in the blood is carried as bicarbonate. And you can see this nicely. Bicarbonate binds to hydrogen ions, producing carbonic acid, releasing carbon dioxide and water. And of course, that carbon dioxide will diffuse through the plasma, through the endothelium, through the brief interstitial space through the alveolar epithelium and out to the alveolus, where it can be exhaled out. And at the same time, oxygen is diffusing through the liquid in the alveolus, the epithelium of the alveolus, the interstitial tissue, the endothelium, the plasma, the erythrocyte, where it binds to hemoglobin, HHB. And when it does this, it knocks off a hydrogen ion. Now, a hydrogen ion can be used to bind with bicarbonate. to release that carbon dioxide. Look at that. Isn't that amazing? And again, we have this concept of the reverse chloride shift, where bicarb goes into the erythrocyte and chloride goes out. So think about this figure and be able to write it in an essay form. Okay, now let's talk a little bit about diffusion and Fick's law. And just like you did for the other laws, I would like you to take this law and make it functional for yourself. So Fick's law states that the rate of gas transfer across a membrane is directly proportional to 1, the surface area of the tissue, to the diffusion constants, which are calculated experimentally, and the difference in partial pressure. That's the driving pressure, if you will, that we talked about when we saw the picture of the alveolus and capillary. The rate of gas transfer across a membrane is inversely proportional to the thickness of the tissue. So if we look at this formula here, diffusion of gas, and here it actually with the dot over the V means flow, is proportional to the surface area times the diffusion constant times the difference in pressure. And this would be the difference between pressure between alveolus and the capillary, if we're talking about that, divided by the thickness. So it's inversely proportional to the thickness. So think about this. What does this actually mean? Can you explain this in your own words using the alveolar capillary membrane? And then we have Graham's law. Here, the rate of diffusion of a gas through a liquid is directly proportional to its solubility coefficient and inversely proportional to the square root of the gram molecular weight. Ooh, do you think you might have to calculate gram molecular weights of some molecules? I think so. So I would definitely start pulling out your chemistry periodic table chart. The diffusion rate of oxygen is greater than carbon dioxide because its gram molecular weight is less. So the gram molecular weight of oxygen is 2 times 16, because we've got two atoms of oxygen in the molecule O2, and this is equal to 32. The gram molecular weight of carbon dioxide is equal to 2 times 16. 16 is gram molecular weight for one oxygen atom, so we've got 2 of them, plus 12, which is the gram molecular weight for carbon. Add them together, that gives you 44. So the diffusion weight for carbon dioxide is equal to the square root of 32, and this gives us 5.6. And the diffusion rate for oxygen is equal to the square root of 44, and that gives us 6.6. So let's start practicing some of this math. So basically what this is saying is that ideally a small molecule should be able to diffuse faster than a large molecule. And then we have Henry's law, which is the amount of gas that dissolves in a liquid at a given temperature is proportional to the partial pressure of gas. So this would be equal to P big AO2 or the P little a CO2. The solubility coefficient is the amount of gas that can be dissolved by 1 milliliter of a given liquid and 1 atmosphere of pressure at a specific temperature. So for example, 37 degrees Celsius and 760 millimeters of mercury, which is equal to 1 atmosphere. Something you might want to memorize, the O2 solubility coefficient is equal to 0.0244 milliliters per millimeters of mercury per milliliters of water. And carbon dioxide, 0.592 milliliters per millimeters of mercury per milliliters of water. Now in this scenario, CO2 is more soluble than oxygen in a liquid medium, such as the AC membrane. In the previous slide, we said that oxygen is probably more easily diffusible because it's smaller. In this slide, we're seeing that carbon dioxide might be actually more soluble, let's say in the liquid surrounding the alveolus or in the interstitial fluid or in the plasma than O2. How can we rectify this? How do we get what we get? Play with this information a little bit. How do we use Graham's law and Henry's law to describe how oxygen and carbon dioxide diffuse at their respective driving pressures through the alveolar capillary membrane? Okay. Now, a little bit about oxyhemoglobin. Now, I'm not going to get a lot into this here because I made another video for you, but oxygen has a limited solubility in the blood. In fact, it's only about 1.5% that's carried as solute or dissolved oxygen in the blood plasma. It is directly proportional to the partial pressure of oxygen. And this gives us a solubility coefficient equal to 0.3 milliliters of oxygen per deciliter of plasma per 100 millimeters of mercury of PO2. Now, generally, this is insignificant at normal PO2. Some people will take this out of the equation for a C little AO2, oxygen carrying capacity, but I don't want you guys to do that. But this solubility coefficient becomes very significant in hyperbaric conditions. So question number 16, what do we use hyperbarics for? Now, as we've mentioned before, the majority of oxygen is transported in blood by hemoglobin. And it's bound to hemoglobin by the reaction of hemoglobin plus 4 oxygen molecules is equal to HbO2 oxyhemoglobin. And this is 1 gram of hemoglobin per 1.34 mils of oxygen. Now, if we look at the figure to the right, this is the heme part of hemoglobin. It's the non-protein active site of hemoglobin. The red represents the iron, and the pink represent the areas that the oxygen can actually bind to. Now, HB often is referred to, I use that just to say hemoglobin, but when you see this in other types of literature, it refers to reduced hemoglobin or deoxygenated hemoglobin. And it gives that blue or cyan color because the iron in the heme is not oxidized, and that's why it doesn't have the red color. HbO2 or oxyhemoglobin is oxygenated hemoglobin. And this is going to be red because of the oxidized iron. We've talked about cyanosis, and I've mentioned before that you have to have a hemoglobin that's high enough to be able to see that cyan color. Now here I put greater than 6 to 8 grams per deciliter. But sometimes you can see it even lower. So I think I've written in your homework 5 grams per deciliter. Now, the binding capacity, just as we mentioned before, is 1 gram of normal hemoglobin binding to a maximum of 1.34 milliliters of O2. This gives us 100% saturation. Now, when we look at this figure, it represents the change in partial pressure of oxygen. And remember, torr also means millimeters of mercury. From the alveolus to the artery, to the capillaries, to the interstitial fluid, through the cytosol of the cell into the mitochondria. And you can see how that is happening, as it goes through the circulatory system. I wonder why. Where are we losing that oxygen? What do you guys think about that? So that's your question number 17. Why does the partial pressure of oxygen decrease so significantly, especially from the capillaries to the mitochondria? And then we have our oxyhemoglobin dissociation curve. And again, I made another video for you, so I'll talk more about that later. But basically, the oxyhemoglobin dissociation curve gives us an idea of how much partial pressure of oxygen is required to maintain a particular saturation on the hemoglobin molecule. So over here, on the y-axis, SO2 represents saturation of hemoglobin molecule, and PO2 represents partial pressure of that partial pressure of oxygen in the serum, in the system. And the black line represents the normal sigmoidal curve. And we're most interested in what we call the P50. And the P50 is the point at which let me get my marker out here. The point at which there is 50% saturation. Okay, so we draw it right here. P50, the partial pressure at which, sorry, my line's not straight, hemoglobin is 50% saturated. And it's about 27 millimeters of mercury. Now, when somebody has a change in their system that increases metabolic demand, then that P50 is going to shift to the right. And what that means is the hemoglobin does not hold on to the oxygen as well. So it doesn't grab on it as well, and it also releases it possibly prematurely. Situations that demonstrate an increase in metabolic demand would be an increase in temperature, an increase in 2,3-DPG. I wonder what 2,3-DPG is, and how does that indicate an increase in metabolic demand? And then an increase in hydrogen ion concentration. So with that, we can make some more, add to this list by saying anything that decreases the pH, because that's going to produce an increase in hydrogen ion, and an increase in carbon dioxide. Now the opposite occurs on the left side, which is the green. If our P50 shifts to the left, that means that the hemoglobin holds on to the oxygen more and is less likely to get rid of it. And situations that will cause a leftward shift are situations that are reflective of a decrease in metabolic demand. So it's basically the exact opposite of what shifts it to the right. So a decrease in temperature, a decrease in 2,3-DPG, a decrease in hydrogen ion, an increase in pH, and a decrease in CO2. Now, carbon monoxide also shifts the oxyhemoglobin curve to the left. And that's because it actually takes up space and impairs the hemoglobin molecule from being able to bind oxygen. Now, your book says that carbon monoxide has a higher affinity for hemoglobin than oxygen, but it's actually more of a structural thing. So what does this mean? Well, if we have a rightward shift of the oxyhemoglobin curve, that means that you might possibly need to increase the FiO2 to increase the PaO2 to ensure that the hemoglobin molecule is saturated properly. If there's a leftward shift, there's not that much you can actually do about that. You got to write it out and fix the underlying problem. And changing oxygen levels is not going to improve anything. So you want to reverse the alkalosis if you can. If the CO2 is low because you're hyperventilating the person, then you need to alter that, etc. Okay, now a little bit about met hemoglobin. This is a situation that also shifts the oxyhemoglobin curve to the left. And what's happening here is that the iron of the heme group is transformed to the non-oxygen binding ferric state. So that means it changed from iron +2 to iron +3. And this occurs by the process of oxidation. And what does oxidation mean? When an electron is lost, then oxidation occurs. Reduction is the opposite. This occurs when an electron is gained. If we don't figure out what's causing the methemoglobin or fix it, then this actually can cause severe hypoxia because the tissue, the tissue is not getting the oxygen because the hemoglobin cannot release the oxygen that's bound to it, causing a significant leftward shift. So what can cause methemoglobin? A common treatment that we give in healthcare, think cardiac. And then what would be the treatment to reverse methemoglobin? Let's see if you guys can come up with this. If you do, I would be very impressed. Excuse me. Okay, and then myoglobin. Myoglobin is the molecule that's involved in carrying oxygen through the interstitium to the tissues, etc., to where it needs to go for the process of oxidative phosphorylation. The myoglobin molecule is basically the leftward shift of the hemoglobin. So it has a super high affinity for oxygen. So there doesn't need to be a partial pressure that's too high or high in order for the myoglobin to be saturated well. So that might go with the question that I asked about, why does the partial pressure of oxygen decrease? And it's okay when we get to the tissue level. Another thing you guys want to look up is rhabdomyolysis. So RHABDOMYOLYSIS, rhabdomyolysis. How does myoglobin play a role in rhabdomyolysis? Excuse me. And then when we talk about fetal hemoglobin, and you'll learn a lot about that in 234, fetal hemoglobin is very similar to myoglobin. The fetal hemoglobin doesn't require a lot of partial pressure for it to be adequately saturated. And this is important because in utero, the arterial blood, or the blood that's really serving the fetus, has a very low PaO2. So I wonder what a normal blood gas would be for a brand new baby just out of the womb. How would it differ from an adult's blood gas, and why? Then we move on to carb-aminohemoglobin. This is carbon dioxide bound to hemoglobin. First, dissolved carbon dioxide, as we saw, is much more soluble in blood than oxygen, but only about 5% of carbon dioxide is transported unchanged, simply dissolved in the plasma. A lot of it is bound to hemoglobin and other plasma proteins. So carbon dioxide combines reversibly with hemoglobin to form carb-aminohemoglobin. It does not bind to iron like oxygen does, but it binds to amino groups, protein groups, peptide groups on the polypeptide chains of hemoglobin, and it does this with other plasma proteins too. So about 10% of carbon dioxide is transported bound to hemoglobin and plasma proteins. Excuse me. But as I mentioned earlier, most of carbon dioxide is carried as bicarbonate. So the majority of carbon dioxide is transported in this way as bicarbonate. So the hydrogen ions formed from the dissociated carbonic acid combine with the hemoglobin in the red blood cells. And we saw a picture of that earlier. From that, the bicarbonate diffuses out of the red blood cell into the plasma, while chloride will diffuse in their place. This is known as the chloride shift, and we talked about this twice now. So your last question, chloride shift, why do we care about that? Chloride shift, or hyperchloremic acidosis, is really the only major type of acidosis that bicarb is a direct treatment for. Why is that? Okay, and that is it for this chemistry. We'll do a little bit more lung mechanics later.